vector fields. The goals in this section to sketch a vector field, number one. Number two, to find the gradient vector field of a function. Okay, so what the heck is a vector field? Well, okay, in words, a vector field f is a function that maps points to vectors. So what would that look like symbolically? We could say f of x, y, two ways to say it. If we're mapping a point in R2 to a vector in R2, then the input would be just x and y. And we could think of the I component as a function of x and y. We'll call it p. So p of x, y times I. And then we could think of the j component as a function of x and y too. We could call that q of x, y times j. Or you'll often see me write it without the function notation, just in component form, saying p comma q, with the understanding that p is a function of both input variables and q is a function of both input variables. And then so we're mapping just a point to a vector, and we really do think of that vector as an arrow here. And if you think about it, what we're actually doing looks a lot like a transformation. We're mapping a point in R2 to something else in R2. But now we're thinking of it with a transformation. Back in 15.9, we mapped a point to a point in the UV plane to a point in the XY plane. Even when we use vector notation, that's what we weren't thinking in terms of arrows. Here we're thinking in terms of arrows. We're mapping a point to an arrow. Okay, so that's the difference. And then that could be done in the plane, as this one suggests. So this would be a vector field in the plane. And then, of course, you could map a point in R3 in space, f of x, y, z, to a vector in space, which you could represent as p of x, y, z for the first component. So p of x, y, z times I plus q of x, y, z times j plus r of x, y, z times k. Or sometimes we like to go back to component form and just keep it simple, p, q, r. With the understanding that p, q, and r are functions of the input variables x, y, and z. Okay, so this would be a vector field in space. So let's look at a few examples. The vector field's a constant. 1i, or just I plus 2j, is the same as 1i plus 2j, or in component form, 1, 2. So you always get the same vector no matter what the input. That's about the easiest vector field I can think of. And the way we map a vector field is we make the input point the tail. Okay? So that's worth writing down. The input, which is x, y, whatever that happens to be, the input is the tail of the vector. Okay? So no matter, I pick a point, let's say that's my input right there. I don't care, what am I, a 1, 2, 3, over 3, up 3, I don't care. But let's say my input is 3, 3. In this, it's only this one I don't care because the vector field is a constant. Doesn't matter. I'm going to go from that tail, I'm going to go right 1 and up 2, right 1, up 2. All the vectors, no matter what the input's going to be, are going to look the same. And so I don't really have to pay much attention to what the input is. Wherever I pick my point, I go over 1, up 2. Over 1, up 2. And so, over 1, up 2, you get this effect that, I don't know, maybe it looks like the current. Maybe it looks like we're modeling the current in the river, and it's all, you know, there's no eddy currents or anything. It's all going in a uniform direction, kind of slanted, like so. Over 1, up 2. That makes sense? Over 1, up 2. So it's super easy to plot a constant vector field. Part B, here we have f of x, y equals y times j, which if you prefer component form, we could express as what? What components would this have?
0,
0, y. So this one we have to think a little bit. So if I made the input 2, 0, what's the vector? Well, what's the y component of this point? Well, I don't want to draw an arrow there. I was about to draw an arrow to point at the point, but that's probably not a good idea. So this point, this input, so if you wanted to make a table, you could, although I won't do that too often. So the input is a point, like x, y, and the output in this case is a vector 0, y, right? Okay. Then if the input is 2, 0, now you can see what the output is. What's the output going to be? The y value is 0. It's 0, 0. So is that a very interesting input? The 0 vector doesn't have any length to it. It's just a dot. So that's a pretty boring input. We should try something else. What if, in other words, one with a non-zero y? So what would say something along the y? I don't think the y, if a y has a non-zero value, it'll map to something. So what would a vector along the y-axis look like? Say at, let's use an input of 0, 1. What would that map to? Same y value no matter what, right? 0, 1. Oh, so the input would map to the corresponding vector with the same coordinates, wouldn't it? That's kind of weird. Okay, so we would, from this, make the input the tail, and then go over 0, up 1. So like that. But what would it look like if we made the input 0, 2? You'd go up the y coordinate. The x coordinate's always 0, right? That's what this says. X coordinate's always 0, so it's always a vector pointing straight up. And its length is going to be basically the length of the y coordinate, right? So it would be the vector 0, 2. So maybe I don't want to do it right there because it looks like it's connected. How about if I input 0, 3, then what should the y coordinate be? So you input 0, 3, that should go to the vector 0, 3, right? So that would be from that input point 0, 3, you go up 1, 2, 3. But then what if you went down? What if you used an input of 0, -1? Then what's the output? A vector 0, -1, right? So it would look, you'd go over 0, but in a down one, wouldn't you? Or if you put in 0, -3, 1, 2, 3, you'd go in the direction of -3, 0, -3. So over 0, down 1, 2, 3. Like that? Does that make sense? What if I made the input, I think you got the idea, but what if I made the input, what is this, 2, -1, 2, 3, 4? Then the x coordinate's always 0. What's the y coordinate? If the input y is -4, -4. So go 1, 2, 3, 4 down there, like that. Or if I input 2, 1, oh, it's going to look, along any horizontal line, they're all going to look the same, aren't they? Ah, now you found a quick way to graph a whole bunch. All right, I think you get the idea, right? Okay, and you could keep doing that the rest of your life, and you wouldn't get the whole vector field, right? So I'll stop on that one. So what is this saying in component form? It's saying if the input is x, y, the output is the vector x, y, right? So, I mean, we could make a table of inputs and outputs, but you don't have to. Just use the graph. So if I made the input, say, 2, 0, then, so the tail would be 2, 0. The tail is the input, and I would go over 2, 1, 2, up 0. like this. Okay? Whereas if I made the input 0, 2, then the tail is at 0, 2, and I would go over 0, up 2. If I made the input negative 2, 0, I would go over negative 2 and up 0. And it ends up then that this is the vector field of vectors that point radially outward. So along any circle of the same radius, in this case, along any circle of radius 2, you're going to get vectors that point outward. The same distance that the tail point is from the origin. So any vector on this circle then is going to point outward like that, and it's going to look kind of like an explosion, except for the fact that as you go out, the vectors get bigger. So if you looked at a circle, if you looked at the points on the circle of radius 1, since a circle of radius 1 has a radius of 1, then any input on that circle is going to go out in the same direction, right and left, the same distance that the vector itself is from the origin. Okay? So in other words, this vector field is a set of vectors that are that go radially out from the origin. The same magnitude that the input is from the origin. It looks something like that. F of x, y, z equals z times j. So let's think about what that would look like. So I'm just going to draw one corner and kind of look at it from above the first octant. So this would be my x-axis, this would be my y, positive x, positive y, positive z. So if you think about this vector field, f of x, y, z equals z times j, then that's the vector field with components 0. What would the middle component actually be? Z, 0. Okay? So here's the thing. If you wanted to select some convenient vectors to draw, one way to do it would be select inputs from the same height, the same z value, right? And then they would all be the same vectors. So let me give you an example. Let's pick points that all have the same z coordinate. A 1. Sorry about that. And then it doesn't matter what the x and y coordinates are. It could be 1, 3 here, 5, negative 8, negative 10, 100 here. The point is, if the z coordinates are all the same, then it'll map to the vector. The output will be a vector with the same z coordinate, because the inputs all have the same z coordinates. So the output for all of these will be the vector 0, 1, 0. Whoops. There we go. Okay? So here's my idea then. Let's go up to a height of 1 and just plot a few of these. I don't expect great detail here. But here's a line at a height of 1. I didn't try to draw a plane at a height of 1. That's too hard to do. Any input on this line then would point basically parallel to j, right? 1 unit long, parallel to j in the y direction. Does that make sense to you? So you pick an input along here, pick a convenient input, right? And say that length in red there is 1 unit long, so that length in red should be, you know, the distance from the origin to the number 1 on the y-axis, and then just make a copy of that along the same height, and make sure you're running parallel with the y-axis. So these should all look like they're the same length. Then I could go, as long as I'm at a height of 1, all my vectors should look like they're at the same length. And you don't want to overdo it, because the more you draw, usually the less good it will look. But you could do another, maybe another line over here at a height of 1 to give it a little perspective. Draw what is supposed to be a horizontal line at a height of 1, going through, within the plane z equals 1, and then draw more copies of this vector. They should all be 1 unit long, parallel to the y-axis, right? So they're copies of j, essentially, the way I've done it here. But if you went up to a height of 2, like let's say you went up to a height of 2, and I'll just do along this line at a height of 2, then all the vectors would be 2 units long. So maybe up to there, along this line, parallel with y, right? And again, I'm not going to draw too many of these. I think we got the idea. If by the way, if the height were a negative height, the vectors would point in the other direction, wouldn't they? Does that give you an idea? Kind of, sort of. It's not a work of art by any stretch of the imagination. Yeah, okay, I should talk about how we use vector fields. Can you guys come up with some examples of how we use vector fields for me? Just off the top of your head, what could we use vector fields to model? I like that. Weather. Have you ever seen a weather map with a bunch of arrows on it? Now, I don't know, if you look at the local weather station, I'm not sure if they do it quite right, but they do show arrows to indicate wind direction, right? But really, if we're going to do a mathematically correct model, you want maybe the length of the arrow to represent the speed of the wind. That would be a velocity field, wouldn't it? Of a wind velocity field would be pretty cool to look at. So maybe a wind velocity field. And we know that vectors are very good at representing velocities, right? Now, you might not make the length of the vector correspond to the true velocity. They might be proportional, right? So if the wind is pointing in that direction, going at 20 miles per hour, then the true length in your scaling might not be 20. But if over here the wind is only 10 miles per hour, you would want to make this one half as long as this one. Okay, so you can make their lengths proportional even if they don't match the units you're using. Okay, what else? What else could vectors represent? Vector fields, rather. How about a gravitational field? Any other fields you guys deal with in physics? Magnetic field. These are called force fields, by the way. And vectors are very good at representing forces. You could have a velocity field, a force field. Anything else you can think of? Oh, there's one more field I forgot to write. The electric field, right? That's a force field. Yeah? What would the gravitational field of the Earth look like? So if you represent the Earth as a dot, you don't have to be totally accurate here, but a vector, how would a vector say here? Let's say the Earth is you're representing the Earth as a point. How would a vector out here, so the vector would point towards the center of the Earth, right? How would the length of that vector compare to a vector further away? It would be greater, right? So this vector out here would be smaller if the length represents the pull of gravity, right? And so you'd have bigger vectors inward. So let me draw that a little bit bigger. So you'd have bigger vectors the closer the input is to Earth. And all the vectors would be pointing towards the middle of the Earth. And on any circle of equal radius with the Earth at the center, theoretically, I mean, this isn't exact, but all the vectors would be pointed towards the center of the Earth and would be the same length. And then out here, the vector lengths would be less, right? So definitely not a great picture, but you get the idea. There is a type of vector field you've already seen a couple chapters ago, and it has to do with this definition. A vector field F is conservative if there is a scalar function f of x, y, z such that you can take del little f, that's the, little f stands for the scalar function. You can take del little f and get the vector field. Okay, so del little f another way we've used to represent it is like this. Remember this symbolism? That's called the gradient, right? Gradient of f. And del f, remember, is the partial with respect to x times I plus partial with respect to y times j plus partial with respect to z times k. Or if it's just two components, it would be f sub xi plus f sub yj. Remember that? So let's do this. Let's find the gradient vector field of f of x, y, z equals the square root of x squared plus y squared plus z squared. Remember, to find del f would be f sub xi plus f sub yj plus f sub zk. So it's like you're back in chapter 14. We're going to find the partials, right? Okay, so what would the partial of f with respect to x be? So you could think of this function, you guys, as x squared plus y squared plus z squared to the 1/2. So what would that be? It'd be 1/2 times the quantity x squared plus y squared plus z squared to what exponent? Negative 1/2, right? Subtract 1, and then multiply by the derivative of what's inside by the chain rule, which would just be 2x. Or the 2's would cancel, and you could write this with x on top over x squared plus y squared plus z squared to the 1/2, but it's kind of nice to write that as a square root. Square root of x squared plus y squared plus z squared on the bottom. Now, can we use kind of a symmetric argument to get the partial with respect to y? What would be on top? Y over that same square root. And what would be on top for the partial with respect to z? Z. So then your gradient vector field, del f, would be just, put I, j, and k in front of these partials and then add them together. So it would be x over square root of x squared plus y squared plus z squared times I plus y over the square root of x squared plus y squared plus z squared times j plus z over the same square root times k. Now, I didn't put del f of x, y, z, but I think that's clear from the context what the inputs are. So that technically is a vector field. It's a very special vector field. Conservative vector fields are very special because just because you have a vector field doesn't mean it has a related scalar function that you can take the gradient of to get it. But when it does, it translates to something very special.